Exploratory data analysis is an important first step on a long way to the final result, be it a statistical inference in a scientific paper or a machine learning algorithm in production. This long way is often bumpy, highly iterative, and time-consuming. However, EDA might be the most important part of data analysis because it helps to generate hypotheses, which then determine the final result. Thus, in this video, I'll provide the simplest and most effective ways to explore data in R, which will significantly speed up your work. Moreover, we'll go one step beyond EDA by starting to test our hypotheses with simple statistical tests. The most effective way to explore data is to create automated reports. Such reports can be created with only one function. There is nothing deep about them, but they provide a very decent exploratory analysis in a few seconds. This is in fact so cool that I made a separate 5 minutes video on it while doing this one. Check it out if you're interested. So here we'll start to explore categorical variables and check the association between them with Fisher's and chi-square tests. We'll quickly create descriptive statistics and explore the distribution of the data with skewness and kurtosis tests. By the way, I'll briefly explain what skewness and kurtosis are, how they are useful, and how to interpret them. After it, we'll explore the normality of distribution with Quantile-Quantile plots and Shapiro-Wilk normality tests. Then we'll compare groups via box plots and non-parametric tests like Mann-Whitney or Kruskal-Wallis. We'll of course explore correlation between numeric variables with different methods, starting with the parametric Pearson and finishing with the non-parametric Kendall correlation. Besides, we'll visualize the correlation coefficients and get confidence intervals and p-values for them. We'll also explore data with simple linear and non-linear models to see whether there are some trends in data. And finally, I'll give you a quick glimpse into how to find, explore, and impute outliers and missing values with different machine learning methods. But here again, I found this topic good on its own and singled it out in another short video. So let's get straight into deep exploration of categorical variables. Simple bar plots with frequency distribution of all categorical variables are already quite useful because they provide a quick overview about the meaningfulness of the categorization and whether there are some typing mistakes in the data. Data Explorer package provides a simple plot bar function which does just that. However, plotting a target discrete variable by another discrete variable is even more useful. It is some sort of visual frequency table. For this, use the by equal argument and give it the second categorical variable. xCatVis function from SmartEDA package also plots each categorical variable with the bar plot, but displays proportions instead of counts. And here we finally come to the deep part of EDA. The plot below nearly screams the hypothesis that education level is strongly associated with the job. Namely, the more educated we get, the more likely we'll end up working with information, for example with data, and the less likely we'll end up to work in the factory. However, without a proper statistical test and a p-value, this hypothesis cannot be tested and remains, well, a speculation. Fortunately, the ggbarstats function from ggstatsplot package does all the above in one line of code and even goes one step further. Namely, it counts and calculates percentages for every category, it visualizes the frequency table in the form of stacked bars, and provides numerous statistical details, including p-value, in addition to visualization, which allows us to make a conclusion or inference already in the exploratory phase of the project. Descriptive statistics is usually needed for either a whole numeric variable or for a numeric variable separated in groups of some categorical variable, like control and treatment. Three functions from the Luca package, namely describe, univar numeric, and diagnose numeric, do totally nail it. Be careful with the describe function though, because it also exists in HMISC and psych packages too. Thus, in order to avoid the confusion, simply write the looker semicolon in front of describe function, which then provides the most common descriptive statistics like counts, number of missing values, mean, standard deviation, standard error of the mean, interquartile range, skewness, kurtosis, and even 17 quantiles. Here we can also see how useful can be collaboration of the Luca with tidyverse packages like dplyr and its group by function, which calculates descriptive statistics per group. And if you don't need such a monstrous table, but only want to have the median instead of 17 quantiles, use univar numeric function. Diagnose numeric function reports the usual 5-number summary, which is actually box plots in a table form, and the number of zeros, negative values, and outliers. Smart EDA with its expnum_stat function provides, in my opinion, the richest and the most comprehensive descriptive statistics table. Moreover, we can choose to describe the whole variables, grouped variables, or even both at the same time. If we call the argument by equal with the big letter A, we'll get statistics for every numeric variable in the dataset. The big G delivers descriptive statistics for groups, but we'll need to specify a group in the next argument gr equal. Using GA would give us both. We can also specify the quantiles we need and identify the lower hinge, upper hinge, and number of outliers if we want to. Summary tools topic can be singled out because functions presented below give you a quick overview about the whole dataset, and some of them also check hypotheses with simple statistical tests. For instance, df_summary function from Summary Tools package provides some basic descriptive stats for numeric and counts with proportions for categorical variables. It even tries to somehow plot the distribution of both, but I didn't find these plots useful. What is useful though is that df_summary provides a number of duplicates and missing values. Table summary function from GT_summary package summarizes all categorical variables by counts and percentages, while all numeric variables by medians and interquartile ranges. The argument by equal inside of this function specifies a grouping variable. The addP function then conducts statistical tests with all variables and provides p-values. For numeric variables, it uses the non-parametric Wilcoxon test for comparing two groups, and the non-parametric Kruskal-Wallis test for more than two groups. Categorical variables are checked with Fisher's exact test if number of observations in any of the group is below 5, or with Pearson chi-square test for more data. Why do we need to explore the distribution? Well, many statistical tests depend on symmetric and normally distributed data. Histograms and density plots allow us the first glimpse on the data. For example, Data Explorer package provides very intuitive functions for getting histograms and density plots for all continuous variables at once, namely plot histogram and plot density. Moreover, they both collaborate perfectly with dplyr package, which is always a good thing. So looking at two variables displayed here, we can see that wind is distributed kind of symmetric while ozone is not. But how can we measure the symmetry of data? And when is the data symmetric enough? This symmetry can be described by two measures, skewness and kurtosis. They are useful because significant skewness and kurtosis clearly indicate not normally distributed data. Skewness measures the lack of symmetry. A data is symmetric if it looks the same to the left and to the right of the central point. The skewness for a perfectly normal distribution is 0, so that any symmetric data should have a skewness near 0. Positive values for the skewness indicate data that are skewed to the right, which means that most of the data is actually on the left side of the plot, like in our ozone plot. Negative values would then indicate skewness to the left, with most of the data being on the right side of the plot. Using skewness function from Moments package shows that the skewness of ozone is indeed positive and is far away from the 0, which suggests that ozone is not normally distributed. But here again, how far from 0 would be far enough in order to say that data is significantly skewed and therefore not normally distributed? Well, Agostino's skewness test from Moments package provides a p-value for that. For instance, a p-value for ozone is small, which rejects the null hypothesis about not skewed data, saying that ozone data is actually significantly skewed. In contrast, the p-value for wind is above the usual significance threshold of 0.05, so that we can treat wind data as not skewed and therefore normal. Kurtosis is the measure of heavy tails or outliers present in the distribution. The kurtosis value for a normal distribution is around 3. Here again, we need to do a proper statistical test which will give us a p-value saying whether kurtosis result is significantly far away from 3. Moments package provides Anscombe-Glynn kurtosis test for that. For instance, ozone has a kurtosis value of 4.1, which is significantly far away from 3, indicating a not normally distributed data and probable presence of outliers. In contrast, the kurtosis for wind is around 3 and the p-value tells us that wind distribution is fine. Now, finally, the normality of the distribution itself can and should be always checked. It's useful because it helps us to determine a correct statistical test. For instance, if the data is normally distributed, we should use parametric tests like t-test or ANOVA. If, however, the data is not normally distributed, we should use non-parametric tests like Mann-Whitney or Kruskal-Wallis. So the normality check is not just another strange statistical concept we need to learn, but it's actually helpful. There are two main ways to check the normality: using a Quantile-Quantile plot and using a proper statistical test. And unfortunately, we need them both. Data Explorer package provides a simple and elegant plot QQ function, which produces Quantile-Quantile plots either for all numeric variables in the dataset or for every group of a categorical variable if the argument by equal is specified. But plot normality function from the Luca package visualizes not only Quantile-Quantile plot, but also the histogram of the original data and histograms of two of the most common transformations of data, namely log and square root transformations, in case the normality assumption wasn't met. This allows us to see whether transformation actually improves something or not, because it's not always the case. Here we could also use deep Lyons index in order to quickly visualize several groups. The QQ plot can be interpreted in following way. If points are situated close to the diagonal line, the data is probably normally distributed. But here we go again, how close is close enough? It's actually very subjective. That is why I like to explore QQ plots using ggpuber package, which goes one step further and shows confidence intervals, which help to decide whether the deviation from normality is big or not. For example, if all or most of the data fall into these confidence intervals, we can conclude that data is normally distributed. However, in order to be sure, we'd need to actually do a statistical test, which is, in most cases, a Shapiro-Wilk normality test. Very intuitive normality function from the Luca package performs Shapiro-Wilk normality test with every numeric variable in the dataset. For example, we have seen that variable wind in air quality dataset has a nice skewness and kurtosis, so it's supposed to be normally distributed, while variable ozone supposed to be not normally distributed, right? And indeed, normality function totally confirms that. Moreover, by the collaboration with the Playa package and its group by function, we can conduct around 2000 normality tests in seconds and only few lines of code. So why don't we just do our Shapiro-Wilk test all the time and forget all those skewnesses and visualizations? Well, because given enough data, Shapiro-Wilk test will always find some non-normality, even in perfectly symmetric bell-shaped data. Here is an example of a vector with less than 300 values where Shapiro-Wilk test shows highly significant deviations from normality, while a density plot shows a bell curve data distribution. Moreover, tests of skewness, kurtosis, and Quantile-Quantile plot all indicate normally distributed data. Thus, it's always better to check several options before making a conclusion about normality of the data. Box plots help us to explore a combination of numeric and categorical variables. Put near each other, box plots show where the distribution of several groups differ. For example, using the intuitive plot box plot function from Data Explorer package with an argument by equal, which specifies a grouping variable, will put all groups of all numeric variables into the boxes. Such exploration, however, immediately creates the next question: do these groups differ significantly? We cannot tell that from just staring at the picture, but if we use a ggBetweenStats function from ggStatsPlots package, we'd check tons of hypotheses using only a few intuitive arguments. For instance, data, x-axis, where we determine the grouping variable, y-axis, where we have our numeric variable of interest, and the type of the test, which I would always set to non-parametric for exploratory analysis. This simple code not only provides you with p-value, which tells you whether there are significant differences between groups, but also conducts a correct multiple pairwise comparisons to see between which groups exactly these differences are. ggBetweenStats function even adjusts the p-value for multiple comparisons with whole method automatically and produces a bunch of other statistical details on top of the amazing visualization. In fact, I found ggBetweenStats function so useful that I did 2 separate videos on it already. In order to quickly check the relationship between numeric variables, we can use correlate function from the Luca package, which delivers correlation coefficients. If we don't specify any target variable or the method, Pearson's correlation between all variables will be calculated pairwisely. The Luca's plot correlate function is a bit more useful because it visualizes these relationships. We can of course determine the method of calculations if we need to, be the default Pearson, or a non-parametric Kendall or Spearman correlations, which are more appropriate for not normally or not very linearly distributed values with some outliers. The shape of each subplot shows the strength of the correlation, while the color shows the direction, where blue is positive and red is negative correlation. It's fine for the pure exploratory analysis, but as always, the next logical step would be to test hypotheses and to figure out which correlations are actually significant. And that's exactly what ggcore math function from ggstatsplot package does. Namely, it displays correlation coefficients, a colored heat map showing positive and negative correlations, and finally shows whether a particular correlation is significant or not, where not significant correlations are simply crossed out. Moreover, we can get the results in a table form with p-values and confidence intervals for correlation coefficients, if we want to, by simply using output equal data frame argument. If any particular correlation catches your attention during the exploratory data analysis and you want to display it professionally, use the ggScatterStats function from ggstatsplot package, which delivers statistical details that matter. Namely, the scatter plot, which helps you to decide to go for a parametric, non-parametric, or even robust correlation analysis, the correlation coefficient itself with the name of the method and 95% confidence intervals, the p-value of the correlation, and even displays the distribution of both numeric variables in different ways. For example, densigram, which combines a density plot and histogram, as you can see on the current plot, or box plots, as you can see in the outcommented line. So you see, in just a few seconds, we went from the exploration of our data to the publication-ready plot with the tested hypothesis, namely, growing ozone concentration leads to a significant increase in temperature. Another effective way to conduct multiple correlation analysis is supported by the chart correlation function from Performance Analytics package. It displays not only correlation coefficients, but also histograms for every particular numeric variable and scatter plots for every combination of numeric variables. Besides, significant stars are particularly useful because they describe the strength of correlation. Here we can of course also specify the method we measure the correlation by. If you don't care about the distribution and the spread of data, but only need correlation coefficients and p-values, you can use core-seq-star function from FastStat package. Compare numeric function from the lookup package examines the relationships between numeric variables with the help of Pearson's correlation and simple linear models. The correlation results are a little boring because they only provide correlation coefficients. However, the results of pairwise linear regressions are interesting because they not only produce p-values but also show other useful metrics like R-squared, IKX information criteria, etc. On top of this, we could plot all the results of compare numeric function, which would display the strength of the correlation with circles, the spread of data with box plots, and the linear regression itself. However, how can we explore whether linear model makes sense at all? Well, I think the easiest way is to plot the data with ggplot2 package and use Guillaume-Smooth function, which always fits the data no matter what shape. Such exploration may point out the necessity to use nonlinear models like GAM or LOS. I found this topic actually so cool that I produced a small separate video on it while doing this one. So, for a deep insight on how to impute numeric and categorical missing values with fancy machine learning methods, check out the other video on my channel. Here, I'll just give you two useful functions from the lookup package. The first one, plot NA intersect, shows you which variables have missing values and how many. And the second function, imputed NA, imputes missing values with different machine learning methods. For instance, using k-nearest neighbors algorithm, we could impute 37 missing values in ozone variable, and even visually check the quality of our imputation in only one line of code. Using the imputed NA function, we only need to specify 4 arguments: the dataset, the variable with missing values, the variable which will predict the missing values, and the imputation method. Check outliers function from performance package provides an easy way to identify and visualize outliers with different methods. If you want to have an aggressive method and clean out a lot of outliers, go with the z-score method. But if you don't have too much data, go with less conservative method, for example, interquartile range. Diagnose outlier function from the lookup package not only counts outliers in every variable using interquartile range method, but also gets their percentages. Moreover, it calculates 3 different averages: the mean of every variable with outliers, without outliers, and the mean of the outliers themselves. In this way, we can see how strong the influence of outliers for every variable actually is. For instance, the variable's depth in Diamond's data has over 2,500 outliers. That's a lot. However, the means with and without outliers are almost identical. Besides, the average of the outliers themselves is very similar to the original average of the whole data. In contrast, the variable price with over 3,500 outliers is heavily influenced by them. The average of the outliers is almost 5 times higher than the average without them. Besides, the looker can visualize the distribution of data with and without outliers, and thanks to collaboration with the player package, we could choose to visualize only variables with over 5% of values being outliers. Similarly to imputed NA function, the looker package also provides the imputed outlier function, which allows us to impute outliers with several methods: mean, median, mode, and cupping. The last one, cupping, is the fanciest, and it imputes the upper outliers with 95th percentile and the bottom outliers with 5th percentile. Wrapping a simple plot command around our result would give us the opportunity to check the quality of our imputation. Alright, that's it for today. If this video provided some value for you, feel free to like and subscribe. Thanks a lot for watching, and we'll catch you again soon in the next video.